Okay, so if we're going to talk about PLCs, the first thing we need to talk about are what are the parts of a PLC, and what is a PLC. So a PLC is programmable logic controller, right? And so it is basically it's an industrially hardened computer that's going to take inputs, whether those be switches or uh, different kinds. Mostly you're going to have some kind of switch coming in, some kind of input that you're going to put into the device, telling it, these are the parameters, these are the things that the machine is doing, and then the machine, you're going to have a program written that's inside of that PLC, and based on what those inputs are telling it, it's going to tell the machine you need to do this or you need to do that. That's kind of the basics of how it works, right? So it's got a power supply. This one's got a communications module. Some of those are built in to the control part. You have the controller module. So the controller module, it's going to be the brain of the PLC, right? That's where your memory chip's going to be. That is where the programming is going to happen. It's where the program is stored. And then you have the I/O system. The I/O system means the input-output system. So I may have a limit switch or a push button out here in the field, right? Those are called field devices. All the things that are physical in the world are field devices. And then those would get wired into my input rack, and that's going to be giving some kind of a digital or analog signal that then the PLC the program is going to interpret what it needs to do based upon whatever the program says. If switch 1 is turned on, I need to turn on this motor. If switch 2 is turned on, I need to turn on this light. If switch 3 is turned on, I need to turn on this pump. If switch 4, which is an e-stop, if that is pressed, everything needs to stop. All operations need to stop. And so all of those things will be wired into this input card and send a signal to tell the program the logic, what does it need to do. And then once the machine has decided what to do, it is going to send a signal to the output card, and then that output card is going to send out a signal into the real world to turn on a motor, to turn on a light, to stop the machine if the machine needs to stop. And so that is the very basics of how a PLC works. All of these things are plugged into a chassis. There's a chassis here that's going to get mounted to the wall or mounted in the cabinet. All of these parts can be plugged in. Some of them are interchangeable, right? Like depending on what kind of outputs I have, what kind of inputs I have, I can plug different modules into that rack to give me a machine that does what I want it to do as the owner of a company. Okay, so the first thing that we're going to talk about is examine if closed, examine if open, and OTE. Those are the three basic instructions for a PLC program. Um, if we take a look at the XIC, it looks a lot like, from your motor control page, a normally open contact, but it's not the same thing. And so in PLCs, this is an examine if closed. And what that means is it's looking for its input. It's looking for a yes or a no. It's looking for a yes, this is passing current through, or no, it is not. So if I have a normally open switch, normally open push button, like from our motor control, and that is attached to the PLC and then brought into the program, right? Then if it's a normally open push button, then it works just like a normally open contact, right? If the contact closes, it passes power through. And so if the switch closes, then it passes power through. But if this examine if closed contact or bit examine if closed bit inside of the PLC, if it's hooked to a normally closed contact, right? Now it's going to light up all the time, right? It's going to be true, like, unless somebody pushes that push button and opens it, right? Because it is receiving a signal, and so it is on. So even though it looks like a normally open contact, right now it is closed because the input coming into it is on. And so that's why we can't rely on normally open and normally closed inside of the PLC program. Inside the PLC program, this is going to be a examine if closed. And so the examine if opened, right, it looks like, well, let's get back to, and it has the line through it. And so it looks like a normally closed contact from motor control, but it's like you have to get out of that thinking when you're thinking about PLC. So in PLCs, this is a examine if closed. This is a examine if open. And so this bit, this internal bit in the PLC program, right? It's something that's going to be programmed into the PLC, right, into the ladder logic. It is looking for a switch or a input, right? It's looking for an input coming into it, right? If that input is off, then it will pass through. So in this case, if we had a push button that were open, right? If that push button were open, then it's looking for it to be open, right? The examine if open is looking for it to be open. So if it is open, then it passes power through. So that's where the difference lies, and so that's where when we're programming in a PLC, we have to get out of the mindset of thinking normally open, normally closed, because how the inputs are wired coming into the PLC itself are going to affect how these examine if open, examine if closed are going to work in the real world. So we need to keep that in mind. And so those are our two inputs. And so this top rung here at the top of the page, this is a representative of a line of ladder logic. So I have an examine if closed, I have an examine if opened, and I have an output energized. That's the third thing that we're going to talk about, right? So our examine if closed and our examine if opened. You guys can't. You got your examine if closed and your examine if opened. These are inputs, right? So I'm going to input some information, yeses or nos, and I'm going to get an output. So if I have this, if this is true, so if the switch that is outside of the program, right? So my switch could be out here that is addressed to this examine if closed. If that switch gets made, then this is true, and if the one that corresponds with this examine if opened, if it is true, then my output energized will become true. So I hope that makes sense to you guys. We're not getting too deeply into what a PLC does, but when my inputs are all true, I have yeses on all of the inputs, and there could be many in this row coming up to this output energized. When all of them are true, my output energized would be true. And each of these things would be addressed. So I would have a examine if closed, and if this if this switch up here were tied onto the PLC, if it was tied into my input rack, if it was tied into screw 00, then this would be input colon 1 or 001 slash 00. And then if I had a limit switch, from your motor control, from your last exam, if I have a limit switch, if it's tied into input 03, then that examine if closed, or it could be an examine open. I could have it as an examine if opened, would be input colon 001, right? Because our input rack is rack 1, and 03, because it is on the third screw. So those are our inputs. Those are inputs that were coming in, right? Could be we could have instead of being a limit switch, it could be a float switch tied to 04. And then that could either be an examine if closed or an examine if opened. And it's going to be I, because it's an input, right? These are inputs. 001 and 04. And so these addresses go with what that input is in the outside world, right? Because all of these symbols, all these symbols that we're putting, these examine if closed, examine if open symbols that we're putting in, are in the program. They're not in the outside world. We have things in the outside world that are coming into the PLC, and then we write a program inside of inside the computer, and we're using these XIC, this XIC 001/00, right? That address, right, tells the PLC to look and see what switch 00 is doing. That address 001/03, it tells the PLC to look and see what the input tied into 03 is doing. And then based upon what it is doing, it takes that information and then it passes it along. And then we use our OTEs, our output energize. They have addresses, right? And so we have, there's an output rack on the PLC that's going to send signal out to, could be a motor or to a solenoid, right? And those are going to be tied in, to 01, 02, 03 on the outputs in the output module. So our output energized, right, it's going to have a name, something like O:2 /1 for a output that's going to that motor. So if this were our program, right, then this, when 00100, when that push button is pressed, then we pass information, right? We're not passing actual electricity because it's inside of a program. We're passing information, passing zeros and ones. So when this is true, this becomes true, and then the program tells the PLC to send actual electricity, to send actual power out to whatever is tied into 01. So that could be a motor, or tells it to send it out to O:203. And so if this one became true, right, that one becomes true, it's going to send actual power out on screw number 3, on screw number 3 to send power out to this solenoid. And that's our XIC, XIO, and OTE. Okay, so next up are bits. But before we talk about the bits, we're going to talk for just another second about outputs. And so we have an output address here, such as O:2 slash, let's just say it's 1, right? So our output here would be written as O:2 slash O1. And so I can use that's an address for this output, right? That's my address for this output. I can a unique thing about PLCs in the way that we can use them internally in the program is because this output is inside the program. Now it is telling the program to do a thing outside of the PLC itself, but it is also working within the program. I can use this address, this O:2 slash 1. I can use that address on an input. And so if I give this bit, this set of contacts, this examine if closed bit or set of contacts, if I give it the O:2 slash O1 address, now anytime that this is true, right? What this examine if closed looks for, right? It looks for the thing at this address. So if I give this examine if closed an output address, then it will examine that output and see if it's on, and if it is on, right? If it is on, then it is true and it will pass power through. And so what I've built here is what's known as a seal-in circuit. So if we have a momentary push button that starts this output and then I release that push button, well, when I momentarily press that push button, my output comes on. My examine if closed contact here in this parallel rung sees that and it turns on. And so then when I release the push button that is controlling this set of contacts, it will leave this one on, and I still have a path for my not so much electricity inside the program, but my information is true, right? This rung is true until someone stops it, right? There should also be a set of contacts in here that I could stop it with, because what I have here now, there's nothing actually to physically, there's not a push button that I can press that will stop this short of turning the PLC off. And so that is another thing that is important about outputs is we can use their address on our input examine if closed and examine if opens. So now that we've got those out of the way, let's talk about the bits. So let me clear out all of this that I've already drawn so that I can concentrate on the bits. And so what a bit is, right, is we have this output, this symbol for the output. And if I give that an address that is a O:2, whatever it is, but if that address starts with an O for output, right, it's going to physically turn on, the PLC is going to physically turn something on. That's not what we always need in the program, right? When we're writing a program, I may want to just have an output that is turning something else on in the program without physically turning something on in the world, right? It's only we want something that's going to give us a yes or no inside the program. And so when we need something like that, then I'm going to use, let me get get a color that you guys will be able to see. I'm going to use a bit. And so a bit is just an address, right? So if you see B3, and then it'll be followed by, you know, a data address. B3 colon 00, could be 02, could be 05, could be B3 colon 5, you know, slash 15, right? It is a address that goes back into a data table inside the program. It's just an internal yes or no, right? And so there's a data table somewhere in the program that is going to look at B300 and it's going to say, is that true right now? Yes or no? And it's going to record a 0 or 1 in that data table, and then you can use that 0 or 1, that yes or no, elsewhere in the program. I could use it here, like we did with the seal in, right? So that I could seal in this part of the circuit. I could also, you know, have it somewhere else in the program. B3 colon 00, and it will actually, you know, start a motor, right? And so I'm going to have an output that is going out to a motor. You know, I can do a lot of things with it, but that when you see that B3, that is an internal bit. It doesn't affect anything in the outside world, right? Because only our outputs are doing that. Our outputs are going out into the world. This B3, it is an internal bit. It's for use within the program. All right, so next up we've got timers. We have 3 different kinds of timers. We've got the timer on, the timer off, and the retentive timer. And so when you see a timer, it's gonna look like this big box here, and you're gonna know which kind it is because at the top it's either gonna say TON for timer on, TOF for timer off, or RTO for retentive timer. Each of those timers has a little different way that it works. You're going to name it. It's going to have to be named T4 colon and then a number 0 up to, you know, 99 or 200. I can't remember exactly what the number is off the top of my head, but you're going to name it a unique number that none of the other timers in the program are named, right? And so it's that number is going to be set by you, because this is like the internal bit we talked about before. This timer is internal to the PLC. It's not a real world asset out there. It's not a real world device. It's inside the program. So its address is the address that you give it. And so we have parameters we have to follow when setting that. And so it's going to be T4 colon. We start with 0, we work our way up and work our way through them until, you know, we've got all of our timers in the program. It's going to have several different time bases, right? This timer is limited by the number of how many pieces of information it can handle in a certain amount of time. The PLCs that we use in our lab, the PLC 500s, that number is 32,756 or something like that. And so it can only count to 32,756. And so if you're counting by ones, right, that's a lot of time, right? If you're counting 1 second at a time, you know, that's going to be, you know, hours. But if you're counting in hundredths of a second, right? If you're counting by hundredths of a second, you're going to get to 32,000 in minutes, not in hours. And you know, some of the newer ones, the 5,000s, you can actually go down to thousandths of a second, and then you're talking about it's only like a 30-second timer. Which, like I said, this is going to depend on which PLC you've got. Some PLC, the timers can count to a higher number, and so you don't have to be as concerned with that as you do in the PLC 500s. But the reason that you're, you know, concerned about that to begin with, right, is how critical is it if you're counting by ones or if you're counting in hundredths of a second. and that's really is just where it, is it something that is critical that you need to count, you need to check that timer every tenth of a second, or is once a second good enough? The preset, right? That's our time base. We're either going to be in one or thousandths of a second, or even smaller increments. Our preset. So this is what we set that timer for. So in this case, this timer is counting to 100 seconds, and so it's counting by in ones, counting to 100 seconds. Once it is done, one of 3 bits is going to come on, right? So when we talk about bits, we had those bit addresses that were B3, right? Those are bits. It's a piece of information, right? So the reason we call those the bits, the B3s, the reason we call them bits is because it's just a piece of information in the program. The same way with the timer, it's just a piece of information in the program, and it has 3 different ones that we can use. We can either use let me get the pen here. I can use T4:0 because this one is 0, and then I have enable, right? And the enable is going to work anytime this timer is on. So if this switch is on to make this timer work, that enables on. This is a timer off. If this switch is energizing this timer, that energize is going to be on. It has a done bit, right? So when this is done counting, whatever it's going to count, that done bit is going to come on the on timer. On the off timer, it works the opposite because the off timer is going to turn something off. So the done bit, when you first energize it, the done bit comes on, and then when you turn it off, then it counts down and turns the done bit off. I don't know if that makes sense, but when you get to PLCs, we'll talk about that. The done bit is energized when the thing is done doing counting to whatever it needs to count to. And then the third bit that we can use, we've got the N. It could be T4:done, and the third one is TT, and TT stands for timer timing. So that's a very useful bit. When our timer is counting, we can have that bit active, and so we can use these to turn things on, right? So I could use this T4: timer timing, and then I could have an output, right, on a rung that T4:0 timer timing, right? Whenever this is timing, it's energizing that output. It could be a motor, could be a light, could be just something that we need to turn on, and that's how that one works. The accumulate right here, that is what it's counted up to so far. So when I toggle this switch, I:00, that accumulate is going to start counting. We're counting by ones here, so we're going to count 1, 2, 3, 4, up until we get to 100. Right? That accumulation is going to continue to go up. If I turn this switch off, right, a regular timer on or a regular timer off, when I deactivate it, it resets that timer. Timer off works a little different. If it starts counting once you take power off of it, but if I re-energize it, then it resets it to 0. Same way, it's going to reset it to 0. If I want to have an application where I run something for a half a minute, and then it stops, and then it starts back up, and then it stops, and it starts, and I want to keep track of that accumulated time. I don't want it to reset every time the timer stops. That's where I use the RTO, the retentive timer. The RTO timer is going to be for when I need to count something in that way. It's enable and done and timer timing bit work just the same way as a regular timer on. The next one we're going to talk about is the counter. You may notice this looks a little bit familiar, right? We have the box, and then we have either a CTU for a count up timer or the CTD for a countdown timer. Once again, we have multiple different bits that we can use with this. I have a CU for count up on a count up timer. I got the done. I have the countdown and the done for the countdown timer. And with this, we also have a reset. And so if this trigger right here, if this switch, we'll switch this out in the real world. It could be a limit switch, a proximity switch, or a push button. Whatever it is, whatever it is that activates this I:20, when this is true, this is going to count up 1. And then it's going to count to 2, and it's going to count to 3. If you notice, both of this is addressed as C5:0. If I address a countdown timer with the same address, then by using this second switch, right, if this switch is activated, it's going to count down 1. So if I had one switch counts up, another switch counts down, it gives me, there's different things I can do with that. But I have a count up for the count up timer. I have a done for the done timer, and that is going to be used just like the other things we've discussed, right? If you had a normally, or not a normally closed, but an examine if opened switch or bit, I could name that with my C5:0, and then I could use one of those other bits. I could use the done bit, I could use the count up bit, I could, I've got those 2 separate bits that I could use to activate some other thing down the line. Now I would obviously I wouldn't put it in line with my countdown timer because I don't want for these to be interfering with each other. But that's how that would get used, right? I'd have a C5:0 and either done or count up or count down if I was wanting to use the one from the countdown timer. We have the same preset, right? So I can change what I want for the done bit to come on at. If I want it to, this works so that right now this done bit is going to come on when the accumulation reaches 5 or greater, right? It is greater than or equal to 5. And so that's what this is looking for. But once it gets started, other than counting back down, you could count back down to 0 by activating this switch. If I wanted to take it all the way back to 0, I need a reset. And so I can set up a switch that's going to use that C5:0. This symbol here is the reset. That reset works on counters. It also works on that retentive timer. On the last page, we talked about a retentive timer that on it, if the switch, when you activate it with the switch, the timer starts. With the retentive timer, if you take that impulse away, it holds whatever time is in it, so that if it gets a pulse again, it just starts back where it was. Well, with that, if you want to get it back to 0, you got to reset it, and so you have to have a reset, and that's what this is. If we put this reset in right here, and we give it the name, just give it the name of whatever we want to reset. So C5:0, or it could be a T4:0 or 1. Then it's going to be reset by whatever input we give it. And so I could give it an input that was, the done bit of another counter or timer. I could give it a reset that was a switch or a push button, right? Like, these are all things that we can do inside the program. We just have to decide to do those things. Okay, so last thing I'm going to talk about with PLCs is the latch and unlatch. And so what a latch or unlatch allows us to do is it allows us to create sort of a permanent switch, the way that you would have, flipping on a light switch, right? So if I press this yellow button at 0.0/1, right? If I were to push that button, it's going to latch in the blue light. And that blue light is going to stay on as long as it has power. That blue light's going to stay on until I unlatch it. Right? So if I, where earlier if we wanted for our output to stay on, I had to build a seal-in circuit here, and use that address, and that address would keep it on. Well, that works fine in certain in most circumstances, really. That works great, and it is a great safety feature because if the PLC loses power, then obviously the thing that is being sealed in right here, it loses power, and when it loses power, then when the PLC is turned back on, that thing's not going to come back on automatically, right? But there are circumstances when you do want that thing to come back on automatically, right? Like if I push the button to start this thing, I want it to stay on indefinitely, right? Until I physically tell it to stop. I want it to be on. Some sort of exhaust fan if it's exhausting, hazardous fumes. If there's a short, a blink in the power and the power goes out momentarily, I don't want for that to turn off my fan. And so I can use a latch to latch that in so that if the power goes out, it comes back on. When the PLC powers back up, that latch is still going to be active. That fan is going to turn back on until I push a button, right? There'll be a separate button that unlatches it. And so if you notice, like these are addressed the same, this latch and unlatch are addressed the same. So if I push the button that activates the unlatch, it will turn off whatever has been latched. And that's how that works, right? And I can label that either as an output, right? So this is output 03, or I could also have this as a bit, right? I could latch in a bit. If I wanted to then use that bit, I then wanted to use that bit to turn off one or more things. So that's the last one we'll talk about today. Hopefully you guys got something out of that. You'll be ready to go for your exam.